Hello, mere bachcho. Welcome back, welcome back. So good to have you all here for another super quick revision session.
Okay, so board exams are coming. I know. And this chapter, motion, is it giving you a little bit of tension? Don't worry, tension mat lo. I'm here and we'll sort it out together.
You know what? In just the next 5 minutes, I promise, we're going to make motion your favorite chapter. Seriously, we'll make it so simple you'll feel like a pro. So, you ready? Let's do this.
Okay, so what is motion, yaar? Let's start with the basics. It sounds super simple, doesn't it? And it is. Just look around you. A bird flying past your window, a car on the road, heck, even the blood flowing inside you. It's all motion.
So the book definition is a bit formal, right? It says an object is in motion when its position changes with time with respect to a reference point. Now, what on earth is a reference point? Think of it this way. You find an amazing new Momo stall, how do you tell your friend where it is? You'd say, "Arey, it's just near the school gate," right? That school gate, that's your reference point. In physics, we just call it the origin. See? So simple.
All right, next level. Let's play a little game. We're going to tackle two words that sound similar but are totally different: distance and displacement. This is where a lot of students can get confused, but you won't. Ready?
So first up, distance. Imagine the meter in your dad's car or scooter. The odometer, it just keeps adding up all the kilometers you travel, right? It doesn't care if you went left, right, or in circles. That's exactly what distance is. It's the total path you've covered. It's just a number. But then there's displacement. Oh, displacement is the smart one. It's like the Google Maps shortest route option. It doesn't care about all the detours you took. It only cares about one thing: the straight line from your starting point to your final point. It's the ultimate shortcut. And, this is important, it always has a direction.
Let's take a proper example. You're going from your house to the cricket ground to play. But wait, you're thirsty. So you take a small turn to the shop to buy a Pepsi. That whole long zigzag path you took, from home to the shop to the ground, that's your distance. But if you draw a straight arrow from your front door directly to the cricket pitch, that is your displacement. Got it? Samajh gaye?
Okay, get your phones ready. This is a perfect screenshot slide for your revision. The key difference: distance is the total path, displacement is the shortest. And check this out. Imagine Usha swims 90 meters in a pool and then swims back 90 meters. Her distance is 180 meters, right? But what's her displacement? It's 0. Why? Because she's right back where she started. Mind blown, right?
Excellent work. So now we know how far things move. The next logical question is, how fast do they move? So let's get into the funda of speed and velocity.
Speed is, well, it's just how fast you're going. The formula is super easy. Total distance divided by the total time taken. Simple. Think about it. Driving on an empty highway at a steady 80 kilometers per hour, that's uniform speed. But driving in peak Mumbai or Delhi traffic, where you stop, go, that's non-uniform speed. And don't forget, the SI unit is meters per second. So then, what's velocity? This is super important, guys. Velocity is just speed with a direction. That's it. That's the only difference, but it's a huge one. If you say a car is moving at 60 kilometers per hour, that's speed. But if you say the car is moving at 60 kilometers per hour towards Delhi, now you're talking about its velocity.
All right, you ready for the fun part? Let's feel the acceleration. Vroom!
What is acceleration? It's simply the rate of change of velocity. The name itself gives it away, right? When you press the accelerator in a car, you speed up. Your velocity changes. It increases. That's positive acceleration. And when you slam the brakes, your velocity decreases. That's also a change, so it's negative acceleration. We also call it retardation or deceleration.
Okay, let's do a quick problem from your textbook, the one about Rahul's bicycle. So first, Rahul starts from rest. That means initial velocity is 0, and he reaches 6 meters per second in 30 seconds. Using our formula, A equals V minus U divided by T, that's 6 minus 0 divided by 30, which gives us 0.2 meters per second squared. Simple. Now for the second part. He applies brakes, and his velocity goes from 6 down to 4 in just 5 seconds. So now acceleration is final velocity, which is 4, minus initial, which was 6, divided by time, 5. So that's minus 2 divided by 5, which is minus 0.4 meters per second squared. See? Not so hard when you break it down.
Okay, next up, graphs. And listen,
Please don't be scared of them. Seriously, think of a graph as a story. It's like a hyperlapse reel you see on Instagram. It tells you the entire story of an object's journey in just one picture. It's a visual summary.
So let's start with the distance time graph. If you see a nice straight line going up like this, what does it mean? It means the object is being very disciplined. It's covering the same amount of distance in the same amount of time again and again. In other words, it's moving at a constant uniform speed.
And here's a golden rule. Write it down. For a distance time graph, the steeper the line, the higher the speed. It's that simple. A very steep line means very fast speed. A less steep line means slower speed.
But what if the line isn't straight? What if it's a curve? Well, a curve means the speed is changing. The object is not being disciplined anymore. It's either speeding up or slowing down. So a curved line on a distance time graph simply means non-uniform speed, which, as we just learned, means there's acceleration happening.
All right, my champions, are you ready? It's time for the final boss battle. We're going to solve a classic exam question. If you get this one right, you're on your way to getting Paka marks in this chapter. Let's do it.
So here's the question. Pay close attention. A farmer moves along the boundary of a square field. Each side is 10 meters long, and it takes him 40 seconds to walk around the whole thing once. The question is, what is his displacement after 2 minutes and 20 seconds? Try to think about it as we go.
First things first, let's draw it out. We have a square field. Let's label the corners A, B, C, and D. And our farmer starts his journey at corner A.
Okay, let's break down the numbers. The side is 10 meters, so the total perimeter is 10 times 4, which is 40 meters. And the question says he takes 40 seconds to cover this. Easy enough. Now, the total time is 2 minutes, 20 seconds. We need to convert that all to seconds, right? So, 2 minutes is 120 seconds. Plus the 20 seconds, that gives us a total time of 140 seconds. Now for the key part. Where is the farmer after 140 seconds? Well, he takes 40 seconds for one round. So in 140 seconds, how many rounds does he complete? We just divide 140 by 40. That gives us 3.5. 3.5 rounds. So after one round, he's at A. 2 rounds back at A. 3 rounds back at A again. And then he does another half a round. Where does that put him? Exactly diagonally opposite at corner C.
So the question asks for displacement, remember, not distance. Displacement is the shortest straight line from the start point, A, to the end point, C. And on a square, that's the diagonal. And how do we find the diagonal of a square? Time to bring in our best friend from math class, Pythagoras' theorem.
So using the theorem, the displacement squared is 10 squared plus 10 squared. That's 100 plus 100, which is 200. So the displacement is the square root of 200, which you can simplify to 10 root 2 meters. And there we have it. That's the final answer. Fantastic job.
And you did it! See? I told you it wasn't so bad. Motion is officially easy peasy lemon squeezy now. We covered everything, what motion is, distance, displacement, speed, velocity, acceleration, the whole shebang. You're all set for your exams now.
But wait, before you go, I have a little challenge question for you, you pro. What would the velocity time graph look like for a car that starts from rest and then moves with a uniform velocity? Think about it. Hey, if you liked this quick revision and it helped you, do me a favor and share it with your friends who might also find it useful. And don't forget to subscribe. Oh, and drop your answer to my challenge question in the comments. I'll be reading them. All right, study hard, and I'll see you in the next one. Bye-bye. Take care.